Section 3, very short, direct continuation of 1 and 2. Why can we make things go faster? Why can we make things go slower? And when I mean things, I mean reactions. Some reactions are very, very quick. Some reactions are very, very slow. And this is the first section of 3 or 4 sections that we're going to be talking about the rate of reactions. And this will lead us into a variety of labs and activities that you will see this stuff in real life, and hopefully it'll be neat for you. In general, there are 2 types of reactions. Homogeneous reaction, which means everything is in the same phase. The reactants are in the same phase. Gas, gas. We don't care what the products are. The products are not reacting. Only the reactants react. If they're in the same phase, it's called homogeneous. They can be both solid, both liquid, both aqueous, and both gas. That's it. Heterogeneous means different phases. The reactants are in different phases. Solid aqueous, solid gas, liquid aqueous, etc., etc. 2 very simple definitions won't be a massive part of this chapter. What we care about is what affects them. We're going to learn what affects them today, and we're going to learn why later on. Few that you know right off the bat. First one is temperature. You've been dealing with this your entire life. Things that are hotter move faster. Massive concept. We'll deal with that in a couple of days. Increase the temperature means you can increase the rate. Decrease the temperature means you can decrease the rate. Same with concentration. Concentration is the amount of reactants present. The more reactants you have present, the faster the rate will go. Massive concept. We'll deal with that in a couple of days. You remove reactants, the rate will decrease. If all of your reactants are gas, instead of concentration, you can say partial pressure. Partial pressure is just of an individual gas. Most of the time, we say concentration, we're referring to something that's aqueous. Okay? Pressure, that will be a new one. Pressure only affects gases. Specifically, it only affects gases in reactants. If you increase the pressure, you will increase the rate if there's a gas. Now there's a couple different ways to increase the pressure. The first way is like number 2. You just pump more gas in. But the second way is decreasing the volume. If you decrease the volume, you're actually increasing the pressure. Okay? We're going to be Italian man hand talker when we deal with this tomorrow. Decrease the volume equals an increase in pressure. And the opposite is also true. If I make the volume larger, then the pressure inside that container will go down. Okay, they're inversely proportional. You're going to have to wrap your heads around that. The fourth one is new. The types of bonds in the reactants will determine how fast or slow the reaction is. If you have a lot of strong bonds, it will take a long time to react. So how do you know if something is strong? How do you know if something is weak? Well, it's very cut and dry in Chem 12. If you have a covalent bond, you instantaneously know it's going to be slow. Covalent bonds are short and very, very strong, which means they're hard to break. So if you have a covalent bond anytime in a reactant, you'll have a slow reaction. Everything else will be fast. There's no such thing as kind of fast, kind of slow, medium fast, medium slow. You're either slow or fast, period. Covalent bonds are slow. Here's another example. Lots of covalent bonds. That's going to be a slow reaction. You've also got 5 of them to break. That's a lot. That's a slow reaction. This next one is the classic trick. Classic. I guarantee you that's on a test and a quiz. H2 and Cl2 you're going to look at and say, hey, there's only one bond there. No brainer. Break them. It's going to be fast. But these are covalent. They're nonmetals. They make a covalent molecule. Very, very slow. Gases are slow. Gases are hard to break, which means we need to look at some phases. So, guess what? Solids are also slow. You take 2 things that are solids and smash them together, you're not going to get a very big reaction. Okay? But if you take things that are aqueous, that are already in ion form, they are looking for something to bond with, that's extremely fast. Gases are slow. Covalent bonds are slow. Solids are slow. Aqueous is fast. That is it, ladies and gentlemen. No other tricks, but you gotta just recognize what you see. Sorry, what is going on here? Something is messed up and I can't scroll down anymore. Oh, that's frustrating. Sorry, guys. In this next reaction, again, it looks fancy. It's called a precipitation reaction. You're going to see these in chapter 3 a little bit more. You see two aqueous ions. It's going to be fast. It doesn't matter if this is a solid, because the solid is a product. Only look at their reactants. Here, we've got an acid-base reaction. Again, it looks fancy. This is some stuff in chapter 4. It's just ions. Those ions are ready to react. They're ready to go. It's going to be very, very fast. Here's a multiple choice question for you, but I can't scroll down. That's frustrating. Oh, man. Give this one a shot. See what you think. I'd like you to tell me which one of these will be the slowest. Okay? A, B, C, or D, which one's the slowest? Then, see if you can problem solve. Try to figure out which one's the fastest. Okay, it's a little harder than it looks, and we'll chat about that in class. We'll chat about that in class tomorrow. There's one more thing that we can do to make a reaction go faster or slower, and that is throw something else in there. Catalysts are a big deal in this chapter. You're going to see them in 4 sections coming up. If you add a catalyst, you're going to make things go faster. That's just the definition, and I'm going to show you a couple reactions in class. It's going to be fun. You add what's called an inhibitor. You're going to make things go slower. Okay, there are a ton of inhibitors, and we'll have some fun talking about these things in class tomorrow. Last but not least, very special example. If you have a heterogeneous reaction, which means if you have something that is different phases, you can change one of the phases. You can make them smaller. You can increase the surface area of one of the phases, and it will help the other phase react with it. Most typical example, I guess, the easiest example I can explain to you is like a liquid and a solid. If you grind up that solid into 1 billion parts, well, then more liquid can hit it, more liquid can react with it, and it'll help. It has to be in different phases, though. Surface area only affects heterogeneous reactions. You make a larger surface area, you'll have a faster reaction rate. So there's a few little summaries here that we can discuss, and you feel free to write these in and fill these in your blanks. We'll review some of this tomorrow. If you're a solid, you're going to be one of the slowest. If you're a gas, you're going to be a little faster, but you're still going to be slow. Reactants that are ionic, reactants that are in ions will always be the fastest. End of story. Okay? How can you increase the rate? Well, temperature, pressure, concentration, and surface area. Temperature will affect all of them. Pressure and volume will deal with gases only. Concentration will be gases and aqueous. And surface area can only affect heterogeneous reactions. You will see a lot of these in class. You're going to see how they affect everything in class. Just a lot of information maybe all at once, but it should work out for you. We'll see you tomorrow.